Okay, thank you, Shamriddhi, for hosting me here, and thanks to all of you for inviting me to present my work here. Okay, so as you can see, I'm going to talk about properties of some inhomogeneous fluid systems, okay? What do I mean by inhomogeneous fluid? Yeah. Now, lexically speaking, an inhomogeneous fluid is a fluid with a spatially varying particle density, which means if you look at rho, it depends on the space coordinate r. So it's a field, yeah? Unlike a homogeneous fluid where the density rho is constant throughout the system. Now, typical examples include interfaces, for example, the liquid-gas interface in case of a single component fluid, or say a liquid-liquid interface in case of a binary liquid mixture. And in both the types of examples, basically the translational symmetry of the system gets broken. And if you look at the density profile at the interface along this, the interfacial region, which basically separates the two phases of the fluid, you see a gradual pronounced change in the density. So this is the liquid phase, this is the vapor phase, and in the interfacial region, which is marked by the yellow color here, you see a sudden change in the density profile. Now, another good example is adsorption of a fluid on a solid substrate or a wall, which exerts an external potential on the particles of the fluid. And this gives rise to the formation of a macroscopically thick surface adsorption layer, and it also leads to the formation of nice density oscillations, which is the characteristic of confined fluid. Moving on, one can also consider fluids which are confined in between, say, two parallel walls or cylindrical geometry, and because of these surfaces have the preferential attraction, you will have surface adsorption properties that I explained to you before.
So suppose the wall didn't have any potential, suppose it was just a thing which blocks, then what will happen to this profile?
So you will still have the oscillations, for sure, but some other properties that you see, they will not be, yeah.
In that plot, this Z, that is the distance along the vertical, the previous slide?
Exactly, yeah. So it's perpendicular to the surface.
It's perpendicular to the surface on which it is.
Exactly, yeah. Yeah, now all these examples.
Yeah, so can you go there?
Yeah.
So 0 is where in that plot, or should I? On the left-hand side, you have a wall and some.
So 0 is here.
And 20 is up?
This is it. Yeah. Now.
So I guess you really had another wall.
Another wall because.
Exactly. Yeah, exactly. So it's better to look at.
Okay, it's more of a
this
confined. So you're thinking of confined. So a few layers of fluids. So it's a narrow confined fluid.
Right. Exactly.
So bulk is really narrow compared to the other.
Exactly. Yeah. Yeah.
Did you say later about why it oscillates near the wall?
This one?
Yeah.
Yeah. So if you look at the total density, it shows oscillations, and that's just because of the packing effect. So
Because of that?
the packing effect. So I mean, this surface prefers, say, the A type of particle, so they go there, and so for the next layer to form, you need to have the separation distance, this particle diameter side. So you have this then the. If I explain it, so basically you have these two walls which are sitting right here, okay? And let's say that these walls prefer the A type of particles. So I have a binary fluid here which is A and B type of particles, and both the walls are preferentially attract A particles. Now this blue data, if you look at it, that's what is the order parameter here, or say the local concentration difference, so which is basically the number of A particles minus number of B particles. Now let's start from the surface here. We know that this surface prefers A particles more. That's why you see if you look at the concentration, it's positive here close to the surface. And then as you go away, decreases. In the bulk, it becomes minimum, and then the same thing for the other surface also. Now the distance over at which it crosses over from the positive value to the negative value, that marks the width of the surface adsorption layer. Yeah. So yeah. Now, since we were talking about single component liquid, maybe I just mentioned here, the difference is that if you take a single component liquid, the order parameter is the density itself. But if you take a binary liquid mixture, then it's the difference. So you get oscillations, yeah. You still get, yeah. Okay, so now, so all these examples that I was talking about, they are quite relevant in nanofluidics, okay? Because typically in nanofluidics, you happen to have a fluid which is in contact with interfaces or some kind of wall with external potential, etc. And these inhomogeneous fluid systems, when they are in conjunction with a continuous phase transition, then you see a plethora of interesting phenomena which you don't see in bulk. And that's what I am interested in, okay? So please remember that in today's talk, we are going to have inhomogeneity in the fluid. That's what I explained. It's a fluid, which means that we are going to have hydrodynamics preservation. So we need mass, momentum, and energy conservation in the system. And it's going to be close to phase transition. So I'll explain what I mean by this. And we take a classical statistical mechanical approach to study this phenomena. And I myself do computational study. So usually molecular dynamics, Monte Carlo, or numerically solving partial differential equations. But in today's talk, I'll just show you some results from the experimental collaborations as well. Not many, but just a few. Okay, so now under this broader umbrella of the inhomogeneous fluids, two particular systems that I have been looking at recently. So in one case, you have a Janus colloidal particle which is suspended in a binary solvent. And when you shine light, laser illumination on this particle, then this particle undergoes active motion. And this particular work, so I'm going to talk about it in detail today. Another thing which I'm working on is something known as Casimir forces and surface critical dynamics. So where basically you take the binary liquid mixture and you put it in between two confining walls, two impenetrable walls, which have a preferential attraction to one of the two components of the fluid. And if you have this symmetry breaking surface field, the surfaces, that affects the static and dynamic quantities of the properties of this fluid, okay? And that's what is known as the surface critical dynamics. And under certain situations, you might get a force which acts on these surfaces, which are known as Casimir forces. But this is the thing which I will talk about in detail tomorrow.
Forces is typically when you're adapting.
No, so this is the classical version. So what?
Classical version.
So yeah. So what you are talking about is the quantum Casimir, where this excitation, the H cross, is the leading factor. In here, basically, it's the KBT that takes the role of H cross. So you have thermal fluctuations in the system. So I have a fluid which is close to the second order phase transition, and I have these surfaces. Now, close to the critical point, this correlation length, the bulk correlation length, is becoming very large. So these fluctuations that I have, if it's such that this separation distance is of the order of the correlation length, then these two walls are getting correlated. And in that situation, if you look at the free energy of the system, you can show that you can decompose it into a bulk part, surface part, plus another contribution. And that another contribution becomes zero when the separation between the two walls is very large, infinity. And that part, it actually shows some scaling behavior, like, close to a critical point, all these static and dynamic quantities show the scaling properties. So this extra term also shows certain scaling relations. And so that's basically the Casimir.
So just to get an idea, supposing I have two plates at the small enough distance within the correlation length, then it scales as some inverse power law of the separation?
Yeah.
And that power, is it,
so
does it depend on the system, or is it universal, or?
Okay, so first of all, if you look at the scaling of this, the extra term, it goes as 1 over L cube. L is the,
Always 1 over L.
it's 1 over L cube.
L is the separation.
Yeah, but whether it's attractive or repulsive, that depends on the geometry and the kind of surfaces you have. If both the surfaces are attracting the same species, what they call symmetric or antisymmetric boundary condition. And the, what was the second thing?
I was just asking
okay,
about
okay.
the power law. If you're saying it's always 1 over L.
Exactly, yeah, in classical. Okay, so
That's the force or the potential?
that's the force.
That's the force.
Yeah. Okay. So now let's now talk about this system basically in detail. And as I told you, one key feature to all these inhomogeneous fluid systems that I study is the presence of critical temperature or a second order phase transition. Okay. So I'll just spend 2 minutes trying to explain what I mean by that. Okay, so phase transitions, like we know from our, earlier school studies, that so matter exists in different forms of phases. So we know, like we see in this cartoon-like picture here, where you see the vapor phase, solid phase, and liquid phase all coexisting with each other. And whenever there is a change from one phase to the other, it's known as the phase transition. Now, to understand it in detail, let's have a look at this picture here. So this represents the phase diagram of a chemical system in the pressure temperature plane. And the 3 different phases are marked here. And the solid lines, they mark the coexistence between 2 different phases. And like you know, that the solid and vapor phases coexist along this sublimation curve, the melting curve for the solid liquid, and finally the vapor pressure curve. Now the point to note here is that unlike this solid liquid coexistence curve, which terminates forever, the liquid gas coexistence curve terminates at a certain point, which is known as the critical point. And at the critical point and beyond it, there's no density difference between the liquid and gas phases of the system. Yeah? So one can always go from the liquid phase to the gas phase without encountering any jump in the density, which is the order parameter in this case. And so that's why, this kind of transition is known as a continuous phase transition. And it's also worth mentioning that even though the order parameter is, so you don't see any jump here, if you take the first derivative of that, which is the second derivative of the free energy, that shows singularity, and that's why a continuous phase transition is known as a second order phase transition. So in today's talk, the fluid that we are going to consider is to be close to this kind of critical point. Okay, so let me now tell you exactly what do we do with these colloidal systems. So this work was motivated by experiments in Stuttgart, where what the authors were doing was that they take a Janus colloidal particle, and it's Janus in the sense that if you look at the right half and the left half of the particle, they have different surface adsorption properties. Okay, now they take the particle and put it in a near critical water-lutein binary liquid mixture. And then they shine laser on it. And what they see is that if the laser intensity is high enough, then this particle starts to undergo an active motion. And at early time, you see the formation of this kind of asymmetric structure around the particle. And you see this kind of layers which form around the Janus particle. Now, after these people did the experiment, so basically this system sort of became like quite hot topic in the active matter community, where assuming that this particle undergoes an active motion, what people were looking at is the different properties of this motion. So the direction of motion, or how it rotates and things like that, and how it changes depends on the particle diameter, etc. What we...
What's the color in this other line in that?
This one? So blue, okay, so it's a binary solvent once again. The green here corresponds to order parameter, which is 0, which means it's the mixed phase. The blue corresponds to, say, the A type of phase, which is positive, and the yellow, the negative. So it's the other.
That is one half of the sphere absorbs species.
Exactly.
and the other doesn't, and you don't need laser for this, right?
You need to heat it up.
You need to heat it up before it's out.
Yeah. And now so I mean, the point is they prepare it with a material such that, so I mean, in this case they take gold, such that when they shine the laser, it's only the cap part, the right part, only that absorbs the light. But the left side and the fluid doesn't absorb light. But you have a heat conduction. So eventually it generates an inhomogeneous temperature gradient.
By rings, you refer to that like arcs.
Yeah, exactly. Yeah. Okay, so now, so the question that we were interested in is, why does the particle move at all at the first place? So what is it that is giving rise to the structure formation, and how is it leading to the motion of the particle? So in particular, we are interested in why these rings form, and then this asymmetric structure that you see here, is it only because of the Janus nature of the colloid, or there is something else? Yeah. So that's what we are going to. How bigger?
Big are these colloids?
Bigger? They do some experiments with micrometer size, micron, some with nanos. So yeah, exactly, depending on what velocity they want. Okay, so before I proceed, let me just tell you briefly why this asymmetric structure that you see there might form. So in this picture here, I show you the phase diagram of the binary solvent that they consider. So as you see, it's a lower critical point, unlike the upper critical point, which typically one considers in theory. And the critical temperature is close to the room temperature, 34 degrees centigrade. So when you take the system and just put it, without shining laser, the liquid is in the homogeneously mixed phase. But then say when you shine laser on it, as I told you, the cap absorbs the light and then the heat conducts. So there is an asymmetric temperature gradient which generates into the nearby the solvent. So it might so happen that part of the solvent actually gets heated up and it enters into the two-phase demixing region, but far away from the colloid, that part might still like to be in the homogeneous phase. So it's a pretty complicated structure formation process which is going on. And as you can see, it's interesting because it's happening under the presence of a temperature gradient, and that too a time-dependent temperature gradient. And that is something which is not really well studied in the literature. I mean, for some of you, if you're familiar with the phase separation literature, you might be thinking what is new to it. What's new is really the presence of this time-dependent temperature gradient for which there is no study. Even the reason? Yeah. So, I mean, we also found it quite... this is, they call it water-lutidine mixture. And yeah. And I mean, the explanation they give is there is some kind of bond formation. And if you... chemical, yeah. And if you heat it up, so then basically it becomes much easier for these bonds to break and for the particles to form the ordered state. Not the particles, sorry, this constituent molecules. And so, but I mean, of course, I don't really understand it so well, how this bond breaks and all. So it's the chemistry. Okay, and the second thing to note here is that this structure that you observe here, it's really local in nature, okay? And it's taking place when you have a symmetry breaking surface field in the system, okay? So then to do the modeling of it, just to bring in an analogy between the experiment and the theoretical modeling that we do. So like I told you, they have a lower critical point, but in the modeling, we are going to consider an upper critical point, like one does in the usual Ginzburg-Landau Hamiltonian picture. So when they basically hit the shine laser and heat up the particles, we are going to basically cool the particles down. And this preferential attraction or the weighting properties of these particles that I was talking about, whether it's hydrophilic or hydrophobic, that's taken into account by considering the surface field. So you will see that if you look at the free energy of the system, you will once again have a surface energy contribution. And this particular system belongs to the something which is known as normal surface universality class, which if you are interested, I can explain you if you want. But for the time being, just keeping that in mind, let's try to.
So, did experiments with this kind of fluids also? Because the one you showed had this here.
Lower critical point, yeah. No. You will get, but they don't take it. And the reason is they say that, so this lower critical point is close to the room temperature. So in experiments, it's much easy for them to control the temperature. Whereas if you have to heat it up, so you need to put in some kind of source of energy. And then if you want to maintain the fluid temperature, it is much more harder in experiments for them. So they prefer a fluid which has a critical point close to the room temperature. What do you mean by that? I mean,
no, I'm saying so that's what in the experimental system, that's the phase diagram.
Exactly, yeah.
But in the theory, you somehow analyze this.
Yeah.
Why don't you just do that? Is it that the equilibrium thing is more difficult for that kind of?
You mean why we don't take this type? One reason is because, I mean, in the literature, so the standard method is to start with an up.
So, is there a different kind of fluid for that kind of system?
Not that we are aware of. Yeah. So,
So this is more, that's why you
exactly, yeah. And ultimately, it's going to depend on the correlation length and critical temperature. So, yeah.
In the visible level theory, you write it for this 1 minus 2 variables, right? Phi 1 minus Na minus Np. Actually, they are coupled, right? So there's Na plus Nb also, and that is sort of discarded, or how do you?
No.
Both the sectors should actually couple to each other.
That's true.
One visible level theory.
Yeah. So.
Assuming in just one field, right?
Yeah. So if you think about it, it ultimately boils down to the fact that you have order parameter conservation. So you will have a continuity equation in the system. So I'll come to that actually. Yeah. So I'll come to the model. Then maybe it will be much easier to discuss. Okay. So now, like I told you, so if you look at the system, you have mainly two fields here. One is the temperature field and the concentration field. And these two fields are coupled to each other and they are changing with time. So to solve the temperature field, what we do is just to solve the normal heat diffusion equation. I mean, I would, please don't worry about this tilde sign here. This is just a kind of non-dimensionalization. But to tell you that if the T tilde is positive, it means that it's higher than the critical temperature, and if it's negative, it means it's lower than the critical temperature. And this term D here, that's the ratio of this the thermal diffusivity to the interdiffusivity. So now let's come to the order parameter field. So for that, we take the usual Cahn-Hilliard-Cook.
Constant across the two things.
The
two species.
Yeah. But yeah, I mean, it is like an assumption that, yeah. So to solve for the order parameter field, we take the usual Cahn-Hilliard approach, where one starts with the, as you know, one starts with the free energy functional, where you see this is the typical, the usual Landau free energy, and in addition to that, you have a square gradient term, which takes care of the interface formation. And now if you have a binary liquid mixture, which means that the total order parameter is conserved, so you will have a continuity equation in the system. So that's what is,
Here, the order parameter is the difference.
It's the difference, yeah. And this, the concentration current is related to the mobility and the chemical potential. And then if you do just a few steps, you finally get this expression where you can express the time dependence of the order parameter in terms of the terms which are appearing in the free energy. Now the thing is, this usual Cahn-Hilliard approach This is done for an isothermal system. So when everywhere in the system the temperature is same. But since we have a temperature gradient, how do we take care of that? Or in other words, how do we take care of the coupling between the temperature field and the concentration field? So to do that as the first order approximation, it enters here. So usually you have this, the constant term A here, it's actually a constant, but then this you just replace it by the temperature field, okay? So that's how the coupling comes into the picture. And
Actually multiply all of the terms.
yeah, in principle you will have the, yeah. So the psi.
You would naively think like you wrote over the F over KT, right? F over K when it's a constant, like in the left hand side, yeah. So normally you would think T multiplies the whole functional. And therefore, if it's not a constant, the T should come in and multiply all the terms in that function.
Yeah, so what we do,
Only the first term.
so what we do is, so we keep KBTC as KBTC. We don't change it.
No,
And
fine.
yeah.
I'm just dimension or whatever you would think if T was, because after all you're weighting it by KT. So you would think that the T should
enter
T is
all the
now a
terms,
function
yeah.
of R and T, it should enter inside this,
All the terms, yeah.
thing and therefore multiply all the terms.
Yeah.
So I'm not quite sure why the justification for multiplying only the first term.
So, I mean, to give you the honest answer, it's because just to begin with as the first approximation. And so, yeah.
There's a regime, for instance, where that will be a good this thing and a good approximation. Is it a regime where the nonlinearities are not important or the grade?
I don't. I mean, so basically, if you say very deep, where you have this the gradient, this interface, so that will be much stronger. Then probably this the presence of this coupling to the other terms might be really important. But if you look at shallow quenches, I'm not sure to what extent if you look at the magnitude, to how much difference it will cause. So to
eventually numerically
do
this, it might be worth
just to check it, yeah. Yeah.
Because in particular, to my mind, that C term, the last term is like a surface tension term. That last C grad.
Okay, yeah,
that
right.
Term. And so, if you change the temperature, they'll start hating or liking each other less, less or more. So, that term should be temperature dependent.
Okay.
I'm just guessing that.
Yeah. So this, that's true. Yeah. So
maybe you can phenomenological. It's anyway phenomenological fluid, and A is something you put which will the phase transition.
So just to
if you change the signs, it and gives you a phase transition.
So you mean the free energy, right?
Yeah. So A, the way you have put it, and I could just say that it's phenomenologically it's the simplest thing.
Exactly. Yeah.
Yeah, for the phase transition, that is in the usual Landau-Ginzburg you put T minus DC. But if you are now, I thought you were looking at the dynamics. So that T tilde is roughly T minus.
It's roughly
T minus DC or something. But now, if you are looking at this thing, so maybe what Abhishek is trying to say is that maybe the T dependence in the other coefficients is not so strong. It is not linear in T tilde, maybe. It is, yeah. But yeah. Okay.
Yeah.
Yeah,
So this we should only do if you are very close to the connection.
Yeah. So that's why I said if you take shallow quenches, it. Okay. Yeah, and this the T1 here, that's actually the quench temperature, and this comes just because of the non-dimensionalization. So it's nothing special. And yeah, then you add noise term. And now the thing is, yeah, what's really important is that the surface preferences. Yeah, so the right part of the colloid prefers one of the phases, and the left one the other one. How do we take that into account? That is taken into account by considering the surface free energy. So in addition to this bulk free energy that I write down here, you can write down the surface free energy, which is given by this expression. And so this, now the terms alpha and h here, they are related to the surface properties, and what they do is that they actually dictate which of the two phases are preferred by the surface and at which strength, okay? And this surface free energy gives rise to a boundary condition, the surface boundary condition, which one needs to take into account while solving the the differential equations. Yeah, so I mean, if you have more questions about this surface free energy, that the different terms, maybe I can explain, or otherwise I just move on now. So the idea is that, yeah, you start with the homogeneous fluid where you don't shine leisure on the particle, and then so you have the homogeneous system, and then you just solve the heat diffusion equation and the equation for the order parameter field, and let's see how things change with
the colloidal particle and the PA, right?
Yeah.
And so the heat conduction is happening where? I mean,
So it's from the right part, they call it cap. So from the right part to the left part, and from the colloid into the solvent.
okay, so the T field is defined everywhere.
Everywhere,
and
yeah.
The psi field is defined
In the fluid,
colloid.
yeah.
With the same D.
No, the D will be different. So D is different, yeah. Yeah. So typically, in the colloid, it's much faster, much.
And the noise is coming there.
Because you are close to the critical point.
Yeah. So you have
Shallow quench, so yeah. Okay. So now first, let's have a look at the temperature profile. So subjected to the boundary condition that you apply, you get temperature profiles which are actually which are different. Now, if you take the boundary condition where basically you said that, far away from the colloid on the outer edges of the confining box, I said no flux boundary condition, then this is what the temperature profile looks like. And if you look at it, so at very late time, so there is an exponential and then T here. Yeah, so at very late time, this term basically drops down, and you will have that everywhere in the system, temperature is close to, equal to the quench temperature. Okay, and
It's radically symmetric solutions are, I mean, the asymmetric also.
mm-hmm.
So what is this only R?
Sorry. What one do you mean? I mean,
your colloid has some asymmetry, right?
mm-hmm.
So now, but you are looking at.
So no, this is in the fluid. This is in the fluid.
You're looking for, I guess, some asymmetric solutions, right? So isn't there phi or something like this theta? I mean,
No, because
don't you expect some asymmetry in the?
if you take Janus, of course, it will then arise.
So what is the, you have the colloidal particle in the fluid?
Yeah.
And then you, what is the, you pump, you put in some like large amount of heat on surface.
On the surface, yeah.
Surface, and then.
And but this the temperature.
There's no asymmetry right on the surface.
Mm-hmm.
Doesn't that affect how?
Okay, so okay, I see the point. do I have that result? I'm not sure. So this profile that you see, this is for a homogeneous colloid. And yeah, I'm just checking if I have the, okay, so no, I don't have it here. Maybe I can show you from the paper. So if you have Janus, of course the temperature. Yeah, yeah. Okay, and so that is being shown here. So this solid, the symbols here correspond to the numerical data. And I'll say just ignore the red curve here. Let's just have a look at the black curve, where you see that here is basically your colloid surface, where we quenched it to a temperature -1, and far away from the colloid, it's still at a high temperature 1. And you see you have a strong temperature gradient in the system. And then as time progresses, the gradient basically decreases, and until and unless in the steady state, you should have a temperature profile which is equal to this T1, the quench temperature everywhere in the system. So now let's have a look at the order parameter profile. Okay, so first of all, let's have a look at the homogeneous colloid, which has a preferential attraction to say one of the two components whose order parameter is positive. Okay, and here what I plot is only those points where the order parameter is positive. So as you see here, from very early time, you have some nice surface adsorption layers which form on top of the surface. Some rings form, and far away from it, you have the usual spinodal-like phase segregation going on. And this, as time progresses, these layers basically get thicker and thicker, and more number of layers form until and unless when these layers reach the outer boundary of the box, then the layers start to break up. Okay, and finally, in the steady state, you will have a situation where you will have only one layer outside surrounding the colloidal particle. Now, the point to note here, what was interesting is that typically you know that in phase separation, when you are at a temperature which is higher than the critical temperature, it's in the homogeneous phase. There is no domain formation, right? But if you have a temperature gradient in this kind of system, we do observe that even at places where the temperature is higher than the critical temperature, you do observe these structures which are forming there. And this is something which was predicted in experiments also in Steve Granick's group long back. And the usual understanding is that it happens because of the Soray effect, or this temperature gradient, which then facilitates the formation of structure also at temperatures far away from the higher than the critical temperature. Okay, so now the next thing is to look at the order parameter profile. Now note that since we have the symmetry here, the spherical symmetry, so this is basically the radially averaged order parameter profile. Now at very early time, you see that almost everywhere in the system, the order parameter is close to the initial value, and you have only one surface adsorption layer. But then as time progresses, you have more surface adsorption layers and depletion layers which are forming in the liquid. Then if you look at the 2-point correlation function, equal time but 2 point, you observe similar oscillations in the correlation function, and that's because basically each ring that forms here, so that actually corresponds to the peaks that you see here. Okay.
So you had a surface terminal interaction. What does that do? That tries to the order parameter at the surface.
Yeah, exactly. So I mean, it has two roles actually. Okay, maybe I just tell it in 2 minutes. Yeah.
Sorry.
No.
Capital R is the radius of the colloid.
So usually, I mean, what happens here in surface critical phenomena, if I have the surface and if I look at the, say in case of the lattice language, if I look at the magnetization or the spins which are there, because of the missing neighbor effect, if I look at the energy on the surface layer, it's much lower than in the bulk. So now, how can you get rid of that? To do that, one way is to increase the coupling between these spins on the surface by a certain factor as compared to in the bulk. And by what factor you increase it, that actually determines which kind of surface universality class the system belongs to. So if if it's larger than a certain critical number, then you will have ordering on the surface as well as ordering in the bulk. And that's what is known as the normal surface universality class. So if you remember those terms that I showed you, C and H, so they make sure the fact that this coupling is larger than the critical number, and so you have the adsorption. Yeah. But then, so if you look at the other term, say for example this H term, so this once again determines which of the two phases will come, because so ultimately when the system tries to go to the equilibrium, it has to minimize the free energy. So if the whole thing has to be negative, now let's say if I want psi to be positive on the surface, I know that the H has to be negative. So that way I can. Okay, so this was something with neutral colloid, which doesn't have any kind of preferential attraction. So I think I'll just skip it and straight away let's go to the Janus colloid. So here in this picture, starting from time t equal to 0 to 400, there is no leisure illumination, so there is no temperature gradient. So whatever structure is happening is purely because of surface adsorption, okay? And this is the steady state profile that you see, which is happening because of the surface enhancement. Now say at 401, I turn on the laser, which means that from 401 onwards, whichever is happening is because of surface adsorption plus temperature gradient. And then you see in the presence of temperature gradient, this structure becomes, the asymmetry becomes really so hugely pronounced. And this will have effect in the active motion of the particle as well, because the stronger the asymmetry, it will move much faster. So that actually relates to the question that I asked, that is it related to only the Janus nature of the particle or there is something else? So indeed the temperature gradient does make things much more pronounced. Okay, so now one good thing about this, the modeling that we did was that even though it was phenomenological, those parameters that entered there, you can relate it to experimentally measurable quantities, like the critical temperature, correlation length, the diffusivity, etc. So there is a way of sort of having a one-to-one correspondence between the experimental parameters and the numerical simulations. So we did some experimental work in collaboration. I won't get into the detail, but just to show you one picture. So these are basically the structures which form around Janus particles. And as you see that these, the rings form here, and with time the rings gets bigger and bigger, and it matches with the experimental results. But I think I'll just skip it. So let's now have a look at the colloid under confinement. So far what we were looking at is when you have the colloid particle put in bulk. But now let's say that we take two glass slabs, two confining surfaces, and let's say that these two surfaces and the colloid surface prefer the same component of the binary fluid, okay? And then let's look at it under two situations, thick film and thin film. Now in thin film, you see that starting from very early time, you have these surface adsorption layers which are forming, which get bigger and bigger. And finally, you get a nice bridge which forms, which actually connects the colloidal particle to the surfaces. Whereas if you take a thick film, the qualitative non-equilibrium dynamics is the same, the formation of these structures and all, but you don't see the formation of any kind of liquid bridge. And why is this important? That's because now imagine if I take one more colloidal particle and put it here, so because of the presence of this liquid bridge, the second particle will then try to go to the first one just because of capillary attraction. So then you will have aggregates of colloidal particles which are forming. Whereas in case of thick film, you don't have any kind of, the bridge, so there is no capillary attraction. So this mechanism then will not be present for the thick film. So one can tune it also to form some kind of colloidal aggregates and cluster formation under confinement.
From the writing figure, as we increase the width of this film, is there a way to study when this solution becomes unstable and start growing this?
Yeah, I think that's. and then it starts to, yeah. So I think that's something interesting one can look at, but we didn't do it so far, yeah. Okay, and please stop, yeah. Okay.
I was just wondering why the time scale here is different from. Yes, you just wanted to show that.
You mean?
You have 200, 500, and that's it.
Okay, so one reason is because it's a thick film, so you need longer time to get the, yeah. Exactly. Yeah. To get everything to the steady state, yeah.
For the thin film, once a bridge forms, you're completely anchored. After that, there is not much happening anymore. You just sort of sweep up.
Exactly, yeah.
So this is also related to what Vishit was asking before about the temperature profile. So similarly here, the density profile that you had shown, with these oscillations. So is there an analogous sort of density for these things?
Yeah, so in this case,
that's Vishit's point about this angular, right?
yeah, now the thing is, in this case, it's the, so what you have is the concentration field. So there is not really, yeah, directly accessing the, yeah. But if one does, say, fluid dynamic simulations, then probably one can have an, yeah, access to it.
No, but presumably you're still solving the confinement, right? So presumably you still have the order parameter field, right?
Yeah, sure, yeah. So if you look at
oscillations, if I remember for the homogeneous colloid was in that order parameter field, right?
it's in the density. In the density.
The difference of the density, right?
No, the no. So the oscillations because of the packing effect, that's in the total density. But and
the homogeneous colloid. Sorry, maybe I misunderstood.
This one. Okay. Okay. Yeah. Right. Yeah. Right. I was thinking about the initial picture that I showed you. Yeah.
So this is for the homogeneous colloid.
This is for
where I understand that it only depends on R on the distance because it's always there. For the Janus colloid, what's the analog of this? There it should depend on psi R comma theta.
Absolutely.
Right?
Absolutely.
But
yeah.
But I mean,
it's quite trivial.
It depends on the geometry of the aspect ratio of the confinement.
It does depend on the say the radius of the particle to some extent, of course, but it's quite straightforward. I mean, yeah. That's what I'm thinking. Maybe at the end of the talk, I can then, yeah. Yeah. Actually, we can do that, yeah. So let's say if this is the order parameter, and I have a Janus particle here. So let's say we are looking at only the part of the fluid which is to the right of the particle. Yeah? And yeah, so then what you see is you will have a surface adsorption layer, depletion, and then it will be close to the bulk. So this is at an early time. Now as time progresses, you will have these things which are shifting to the right, and you might also have another small layer which is forming. The reason it's shifting is because as time progresses, the width of that ring also increases, the surface adsorption layer. Yeah, so that's why they basically shift rightwards. And yeah, so then if you wait for a long time, then the final equilibrium profile will be that you will have only one thick layer, one big ring, and then just the. Huh?
zero is fine.
0 you can say somewhere here. So that's why in the equilibrium case, because it's positive, here it, the overall one, yeah.
Sorry, and also now this colloid is moving, right? It's active. Okay, so this I would try to think about in the frame of the colloid. If I'm sitting on the colloid, this is colloid.
Exactly, yeah. But then also the thing is, if the colloid is moving, you are not really giving it enough time for all these rings to form. So, yeah, yeah, yeah. Okay, so yeah, and then to just to end it with yeah.
So these part parameters that you've used, how fast do they move? For example, if I'm thinking of this, extent of what I see there on the picture, how long will it take from it to go from one end to the other?
So I mean,
Exactly. So
yeah, sure, yeah. So I mean, in experiments, so depends on the leisure intensity, of course. Yeah. Say if the leisure intensity is around 10 microwatt per micrometer square, velocity is around 0.6 to 0.8 micrometer per second. So yeah, I would say it's quite fast.
The radius of the colloid is about 1 micrometer, you said?
12 micrometer.
12
micrometer. So yeah.
Not very slow, right?
Huh?
Presumably that's not very slow. Because it seems to cross its radius in very fast. And
it's directed, yeah. Okay, yeah. So then just to show you some final result on the motion of the particle. So, so here in this picture, I plot the velocity of the particle as a function of the this temperature gradient that is imposed. And as you see, when the temperature gradient is small, the velocity is small as expected because the concentration gradient is smaller. And then as you increase the temperature gradient, the velocity also increases. Now, what's interesting is that if you look at the same thing for a phobic philic colloid, you see that up to a certain temperature gradient, velocity is negative, which means say the particle is moving in this direction. Beyond a certain threshold, suddenly the velocity becomes positive. So the particle changes its direction and starts moving in the opposite direction. And this is something we don't still understand why it's like that. But we have a sort of intuitive idea that probably it's related to this structure which is forming, and it's related to the isotherm. So if you look at the very, the low temperature thing, and you see that the isotherm has not covered even the half of the particle. Whereas if you keep on increasing the temperature gradient, you might have a situation where the isotherm, the critical isotherm, has covered almost all of the particle and it sits here. So then clearly, if you look at the concentration gradient around the particle, probably it's going to be different, and somehow that's related to the the direction of the velocity. Okay, so to calculate the velocity, that's with hydrodynamics. So we use the Stokes equation. Yeah, so I didn't want to include the details. It's phoretic. Phoretic. So you have a gradient here in the concentration. Yeah. And
then just the gradient.
Yeah. I mean, because you have a temperature gradient, you might have a contribution which is coming from that also, which is known as thermophoresis. But as we found out, it's pretty small here. Yeah. Mainly the chemical composition. Yeah. Okay.
Unless the chemical composition goes somehow non-monotonically with this, you won't expect the direction to change.
Exactly. Yeah.
It has to keep going more and more and more.
Yeah, yeah. So, I mean, yeah, we don't know yet. But then also, I mean, what is interesting, they found it in the experiments also. So it's not an artifact of the simulation, but what is the actual physical mechanism? Okay. So then, so mainly this is what I wanted to talk to you about. And then, like I told you that I also do something on confined fluids. So for example, say these colloidal particles that we are considering. Now say if I take two colloidal particles, yeah, and I have the fluid in between, and I want to study the dynamics of this particle. So dynamics of the fluid. So how will I do that? One easy approach is to assume that the separation distance is small so that you can treat these particles as parallel walls. And so it boils down to the fact that you have a fluid which is in between two, yeah, in a slit geometry. So it becomes much easier to do the MD simulation. And why you need MD simulation? Because we want to look at dynamics. So Monte Carlo is not enough. We need to have, yeah. So now the thing is, so if you are close to the critical temperature and you are looking at different transport properties of the system, they show some kind of singular behavior. And this singularity comes because when you are close to the critical temperature, you have these large correlating blobs, which means that the relaxation time becomes very large. And if the relaxation time becomes very large, it means that the diffusion in the system, that becomes very small. And then we know that if you look at the correct diffusivity, which in this case is the mutual diffusivity, not the single particle diffusivity, because you have everything is correlated in the system, that shows some singular behavior with a certain exponent, etc. And what we look at is you know, to study the non-equilibrium behavior of this fluid. As a first step, one needs to have an idea of how these transport quantities behave in equilibrium. Okay, so I'll just give you one example here. The rest of the things I'll explain tomorrow. So one transport quantity we look at is the interdiffusivity, which is basically, it's related to the concentration current in the system. Okay, and so it's defined here. So you can calculate the, it's something known as the Onsager coefficient. So you can calculate it either using the relevant Green-Kubo formula or the corresponding Einstein formula as well. And what I plot here is the mean square displacement as a function of time. And as you see, at very early time, you actually see that is squared the ballistic regime. And then at late time, it crosses over to the usual diffusive regime, and from which you can actually calculate this, the equilibrium value of this, the interdiffusion constant. So I'm almost close to the end of my talk, and so I thought to show you what we really mean by this ballistic regime or the diffusive regime. So basically in the ballistic regime, it's like if you consider just one particle, it's sort of like being caged by the other particles which are there. So it's undergoing a free motion, and there we know that the velocity is proportional to time. So if you then look at the displacement is proportional to time. So if you look at the mean square displacement, it goes as t square, whereas in the diffusive regime, as we know, it's the Brownian motion, and you get the linear behavior. Can we please have the video? Yeah. So this is a video from one of Charlie Chaplin's movies, and as you can see, initially he will undergo a ballistic regime. Okay. See, it's caged. And now the diffusion will come, the diffusive regime. So it's diffusive now. And then it goes to subdiffusive also. Yeah. But I mean, what's really interesting, the alcohol bottle doesn't fall. So, I don't know how he did that. Yeah, so I'll just stop it. So the space button, right? Yeah. And escape, yeah. This was Tempo's mod, yeah. Yeah, so I mean, yeah, so if you want to know more about Charlie Chaplin's work, please come to my talk tomorrow. So that's all I wanted to present to you. And yeah, I mean, since I'm here. Yes.
No, the preacher.
That I'll describe tomorrow. Yeah. And yes, I mean, since I'm here for a couple of days, I thought I'll just flash upon the other kind of works that I'm doing, so that if you are interested, we can talk about it. So one thing we look at is something known as coalescence preference dynamics, okay? So it has to do when two droplets or two bubbles, say, come to each other, they collide, and then finally you have a final product drop forms. And it's known from the Laplace pressure difference that the final drop will form close to the bigger of the parents. But the question is, how close to the bigger parent it forms? Yeah, and then if you look at the literature, there is a prediction that if you look at the distance of the final product from the larger one or the smaller one, that depends on the ratio of the diameter ratio of this the two particles. Yeah, and there is some power law behavior. So now the question is, if you take different kinds of systems, say for example, vapor liquid system or say binary droplets, do they exhibit the same exponent of Q, or as in, are they really universal in nature, or what's really going on? So this is something which I'm interested in. And these things which I was studying during PhD, so it was about the nucleation phenomena. So if you take an off-critical fluid, and by off-critical I mean that if you look at the phase diagram of, say, a vapor liquid system, if you are at the critical density, you see the percolating structures. But if you are close to the vapor, this coexistence curves, which means you are off-critical, then you have the nucleation of, this one of the phases, and you see that these things then just grow with time. And the question was, what is the dynamics of this collision? So there were basically two predictions. One was by Binder and Stoffer, where they predicted that they undergo Brownian motion, less collision, and then just the coagulation. And then there was some prediction by Tanaka, where he told that no, it's not Brownian motion, but you're going to have some kind of interdroplet interaction. And we wanted to look at in which situation this will be Brownian motion, on where the interdroplet interaction is going to be more prevalent and things like that. Something else which I was also working on is now known as aging phenomena. So that has to do with the fact that when you have a fluid which is undergoing a non-equilibrium relaxation, one way to look at it is to calculate the two-time autocorrelation function. And then one poses the questions that if you look at this autocorrelation function and you calculate it, for different waiting times, how do they behave? So do they exhibit any scaling, or is it power law behavior, or exponential, whatever? So so mainly this is what I wanted to talk about. So thank you.